When a multinational corporation decides where to build a multi-million-dollar industrial factory, the financial risks are enormous. To solve these massive logistical puzzles, analysts use multi-criteria decision-making, relying heavily on a specific algorithm called the Analytic Hierarchy Process, or AHP. It takes a massive choice and deconstructs it into a hierarchy, a central goal at the top, branching down into criteria like cost and visibility, which then split into the final alternatives. The engine of this algorithm relies on committees of people sitting in rooms, making what are known as pairwise comparisons. They systematically weigh the importance of one single criterion directly against another. The math calculates a clear, definitive winner. But the success of a massive capital project ultimately depends on how accurately those human preferences translate into cold mathematics. The traditional AHP model relies on a 1-to-9 scoring system introduced by Thomas Soddy. It demands that a decision maker assign an absolute, crisp numerical value to exactly how much they prefer one option over another. The physical world and human emotions do not operate in crisp integers. Our judgment is filled with vague concepts and shifting priorities, making absolute numerical precision impossible. This bar chart ranks 3 options based on traditional AHP calculations. When we introduce a 4th, lower-tier option to the dataset, the top 2 ranked bars inexplicably swap places. This is called rank reversal. It happens because rigid integer math breaks when it attempts to process the natural ambiguity of human priorities. When these contradictions occur, the traditional model flags a consistency error. It assumes the human was wrong, rather than recognizing that the algorithm itself is too brittle to handle the data. Forcing people to pick rigid numbers doesn't generate perfect data. It produces fragile mathematics that shatter the moment complexity increases. To solve this, researchers Lotfi-Zadeh, Didier Dubois, and Henri Prade stopped trying to eliminate vagueness. They realized algorithms needed to actively embrace it. Instead of plotting a preference as a single rigid dot, they replaced it with a triangular fuzzy number, a shape charting an entire range of possibilities. This triangle has 3 coordinates: the lower boundary, the modal value in the center, and the upper boundary. This is equation 12-1. It is a rigorously defined piecewise function that captures the exact spread of human uncertainty. A stakeholder no longer has to declare that visibility is exactly a 3 on a scale compared to cost. They can state it is moderately more important, give or take, and the system maps that exact sentiment. By abandoning false specifics and plotting a defined range of probability, mathematics finally learns to speak the language of human uncertainty. When we apply this to the corporate decision matrix from earlier, every crisp digit morphs into overlapping triangles. Each pairwise comparison now functions as a mathematical ratio of these overlapping boundaries. To process this density of information simultaneously, the algorithm runs an approximation eigenvector approach, calculating the weights of all the overlapping boundaries at once. The vagueness resolves into a clean, prioritized list of fuzzy preference scores for each alternative, complete with variance bars. The matrix actively digests the ambiguity, outputting a mathematically sound decision that entirely avoids the trap of rank reversal. When researchers test fuzzy AHP and its revised variations against traditional models, contradiction rates plummet. The algorithm successfully identifies the true optimal alternatives, ensuring the final rankings remain stable even as new variables are introduced. For decades, performing these eigenvector approximations required grueling manual matrix arithmetic, which kept the methodology confined to academic journals. Today, researchers have built self-contained web calculators. A standard browser sorts the variables instantly, democratizing the entire process. The barrier to robust mathematical decision-making has shifted from raw computational power to accessible user interface design. While equipping matrices with fuzzy logic solves complex corporate logistics, it also demonstrates a broader shift in computer science. It highlights a move toward building systems that accommodate our natural ambiguity, rather than demanding we process information like a binary machine. The true triumph of these algorithms isn't turning people into precise calculators. It's teaching mathematics how to navigate the beautifully imprecise nature of being human.